If you were to crack open your laptop right now, you might actually be pretty shocked.
Oh, I guarantee most people would be.
Yeah, because if you look inside, like almost 60 to 70% of the space inside isn't even computing hardware at all.
Right.
It's literally just a giant chemical pouch.
Right.
And I mean, we carry these devices everywhere, right? We rely on them to run, our entire professional lives, our personal lives.
Totally.
But for the vast majority of us, what actually happens under the keyboard is just a total mystery. It's basically treated like a black box that just magically works until the day it suddenly doesn't.
Well, and it is a black box, right? But it's a black box built on a massive engineering contradiction.
How do you mean?
Well, think about what manufacturers are actually tasked with doing. They have to put a high-performance computing platform, something that can, render video, run complex databases, keep 50 browser tabs open.
Which I am definitely guilty of.
Right, we all are. But they have to cram all that into a portable, battery-powered system that you can literally just slide into a messenger bag.
Right. Which takes a lot of work.
Exactly. Solving that contradiction requires basically aggressive miniaturization. Every single component has to be engineered to these highly precise physical specifications.
Like down to the millimeter.
Down to the fraction of a millimeter. And while that precision is what makes modern laptops incredibly capable, it introduces some really unique, often incredibly frustrating challenges for troubleshooting and repair.
Because it's not a desktop.
Exactly. You can't just reach in and swap a generic part like you might on a bulky desktop tower. Everything is custom.
So today we are taking a deep dive into the literal guts of that machine to decode some of those challenges. We're looking through the notes from Professor Messer's CompTIA Plus certification training course.
Specifically, the laptop hardware section.
Right. And the mission here for this deep dive is to give you the inside scoop on the precise engineering inside your computer. We want to, demystify the hardware so you feel empowered, not intimidated the next time your system acts up or when you're evaluating a new purchase.
Yeah, and to understand how any of this hardware functions, we really have to start with what I call the modularity lottery.
The modularity lottery, I like that.
Yeah, because it's heavily dictated by those space constraints we were talking about. Manufacturers handle internal real estate in radically different ways.
Right.
So some engineer their systems so you can, easily access the inside to replace parts. But others build the chassis so tightly using adhesives and proprietary screws that getting inside without specialized tools is just nearly impossible.
Right. And the most critical battleground for that lottery is the power plant itself, right? The battery.
Absolutely.
Okay, let's unpack this. Because looking through the A-plus materials, buying a laptop really feels a bit like buying a car.
That's a great way to look at it.
Yeah, because some cars, have a hood that pops right open.
Yeah.
You see the engine, you can check the oil, you can swap out a battery on your driveway in 10 minutes.
Right. The DIY dream.
Exactly. But then other cars feel like the hood is practically welded shut. If anything goes wrong, you are entirely at the mercy of the manufacturer's authorized service center.
The comparison holds up perfectly. In the laptop world, batteries highlight this divide better than anything else. You have modular batteries, which are becoming way less common, but they do still exist in some enterprise machines.
Those are the ones where you just hit a switch on the bottom.
Yeah, exactly. You press a release latch on the bottom casing, pop the old battery out, and just slide a new one right in. Easy.
But that's not what most of us have anymore.
No, not at all. Most of us have built-in batteries, and these are buried inside the chassis, often underneath other components, or even worse, glued directly to the aluminum casing so they don't shift around.
Oh, wow. So you have to unglue it.
Yeah, replacing them requires completely dismantling the system, delicately disconnecting these tiny ribbon cables, and sometimes literally using chemical solvents to dissolve the adhesive. It's intense.
And the physical shape of these batteries has totally changed, too. I mean, they don't look like a row of AA batteries wrapped in plastic anymore. They look like, flat, black, squishy floor mats.
Yeah, they do. And that shift in form factor is entirely due to battery chemistry. Modern laptops primarily use lithium-ion or lithium-ion polymer.
Okay, and polymer is the squishy one.
Basically, yeah. Lithium-ion polymer is particularly crucial for those really thin and light laptops because it uses a solid or gel-like electrolyte rather than a liquid.
Right.
So that chemical makeup allows manufacturers to mold the battery into these flat, flexible pouches that can literally just be squeezed into all the weird, irregular, empty spaces around the motherboard and the cooling fans.
Which totally explains why you can't just go buy a universal laptop battery off the shelf at a big box store.
Oh, definitely not.
Yeah, the notes point out that you must use the exact make and model for your specific laptop. Because it's not just about the voltage, right? It's about the physical geometry.
Exactly. A battery designed for one chassis physically will not fit into the millimeter precise gaps of another chassis. It just won't work.
Right. And while we're on the topic of batteries, we really should clarify how to actually treat them.
Yeah.
Because old tech myths die really hard.
Oh, they definitely do.
Yeah, like if you are still draining your laptop battery all the way down to zero because you're worried about the memory effect, you are actually doing more harm than good.
Yes. Thank you for bringing that up.
The memory effect, that was the idea that if you plugged your laptop in when it was at, say, 50%, the battery would somehow forget the other half of its capacity, right?
Exactly. And to be fair, older nickel-cadmium batteries actually did suffer from that. They had a crystallization process that effectively reduced their capacity if you didn't fully discharge them.
But not anymore.
No. Modern lithium-ion and lithium-ion polymer batteries operate on completely different chemical principles. They do not have a memory effect at all.
We'll plug it in whenever.
You can, and you absolutely should, recharge them at any time. Deeply discharging a lithium-based battery down to zero on a regular basis can actually degrade the chemical integrity of the cells way faster.
That is so good to know. So because the battery demands so much, volumetric space inside the chassis, it really dictates the engineering of everything sitting directly above it.
Yeah, absolutely.
And most notably, that means the keyboard, which, let's be honest, is the front line of wear and tear.
Oh, without a doubt.
I mean, it takes every spill, every crumb, and just the physical impact of thousands of keystrokes a day.
It's the most heavily abused external component, and logically, it's the one swapped out most often by IT departments everywhere.
I bet.
A laptop keyboard is really a highly complex tapestry. Manufacturers have to cram in the standard QWERTY layout, secondary windows or command keys, function keys for screen brightness and volume.
And sometimes a numeric keypad if you're lucky.
Right, a compressed numeric keypad. And they have to achieve all of this in a tiny fraction of the vertical depth of a standard desktop keyboard.
Well, let me push back on the repair process here, though.
Okay.
Because I have a mechanical desktop keyboard at home, and if I break the E key, I just take a little plastic tool, pull the keycap off, and snap a new one right onto the mechanical switch. Takes 2 seconds.
Sure.
But if an individual keycap breaks on my laptop, the notes seem to suggest replacing the entire keyboard unit rather than just, popping the keycap back on. Why not just pry it off and replace it?
I mean, if you pry a laptop keycap off with a butter knife or some generic tool, you will almost certainly destroy the switch mechanism underneath.
Really? Just from popping it off?
Yeah. On a desktop keyboard, the keys sit on robust, independent plastic stalks with heavy metal springs. But laptop keyboards rely on miniaturized scissor switches.
Scissor switches, right?
Yeah. Underneath that thin plastic keycap are two interlocking, really microscopic pieces of fragile plastic that cross like an X, and they rest right over a tiny rubber dome.
Ah, so if you pull up at the wrong angle...
You snap the microscopic plastic hinges
Good.
immediately.
Wow.
Yeah, the retention clips are delicate just by necessity of the size. I mean, if you absolutely must replace a single laptop keycap, you have to follow the manufacturer's microscopic tolerances and instructions to the letter.
Which most people won't do.
Right. And in an IT environment, the labor cost and the risk of failure mean it's just vastly more efficient to replace the entire keyboard assembly.
That makes sense. And the source notes mention that despite this fragility, replacing the whole unit is surprisingly elegant on a lot of models.
It really is.
Like you just pry off a plastic bezel around the edge, remove a few tiny screws, and the entire keyboard just lifts away.
Exactly.
And it's connected to the main system board by this wide, flat ribbon cable.
Right. That flat cable connects to a ZIF, or zero insertion force connector, on the motherboard.
Zero insertion force.
Yeah, meaning you don't shove it in, you lift a tiny locking flap, slide the incredibly thin ribbon cable out, slide the new one in, and just snap the flap down. No soldering required at all.
Okay, but before anyone even orders a replacement keyboard, the CompTIA notes offer a really vital troubleshooting step.
Oh, this is a lifesaver.
Yeah. It says if your keyboard starts typing double letters, or if certain keys randomly just stop registering, just plug a standard USB keyboard into the side of the laptop first.
Right, because isolating the variable is rule number 1 in hardware diagnostics.
Right.
If you plug in a USB keyboard and it types perfectly, well, you've confirmed a physical hardware failure in the laptop's built-in keyboard assembly.
Right, because the external one works.
Exactly. But if the external USB keyboard also types double letters, then you're dealing with an operating system glitch, or a corrupted driver, or maybe even a malicious script.
Which means buying a new keyboard is a waste of money.
Completely. Buying and installing a new physical keyboard won't fix a software problem.
Right. So this relentless drive to shave millimeters off component heights, it isn't just about external interfaces like keyboards. It completely dictates the internal processing architecture, too.
Yeah, absolutely.
Like, look at the memory. On a desktop motherboard, RAM sits in these long, vertically protruding sticks.
Yep.
Obviously, you can't have a piece of circuit board sticking 2 inches straight up inside a laptop that is only, like, half an inch thick to begin with.
Right. Physics just won't allow it. So laptops utilize a standard called SODIMM, which stands for Small Outline Dual Inline Memory Module.
So dim.
Yeah. It is essentially a compacted, physically shorter version of standard desktop memory. The pins are packed much closer together, and the chips are laid out horizontally instead of vertically.
And SODIMMs participate heavily in that modularity lottery we discussed earlier, right?
They really do. In a traditional modular setup, accessing the RAM is relatively straightforward.
You just pop open a panel.
Yeah, you might remove a small access panel on the bottom of the laptop. And the SODIMM stick sits horizontally, flat against the motherboard. Okay.
You pull apart 2 metal retention clips on either side, and the stick springs up at, like, a 45-degree angle.
Oh, that's satisfying.
It is. Then you just pull it out, slide a new higher capacity stick into the slot at the exact same angle, and press it down flat until the clips snap back into place.
But, and there's always a but, increasingly, manufacturers are bypassing SODIMMs entirely and just soldering the memory chips directly onto the motherboard.
Yeah, and soldering memory removes the need for the physical plastic slot and those metal retention clips.
So they save space.
Exactly. That saves a few precious millimeters of vertical height, allowing for a thinner laptop. It also slightly reduces the physical distance the electrical signals have to travel between the processor and the memory, which is a tiny performance bump.
But the trade-off is pretty huge.
The trade-off is absolute permanence.
Right.
If you buy a laptop with 8 gigabytes of soldered RAM, and then your workflow changes a year later, say you start needing 16 gigabytes for virtual machines or video editing, you cannot upgrade.
You're just stuck. You're stuck. You would have to replace the entire system board, which is effectively the cost of a brand new computer.
Wow. And that space-saving logic reaches its absolute peak when we look at long-term storage.
Oh, definitely.
According to the notes, upgrading one specific storage component alters the entire computing experience literally more drastically than any other hardware swap. We were talking about moving from traditional hard disk drives to solid-state drives.
The engineering leap here is just profound. For years, laptops utilized 2.5-inch mechanical hard drives.
Those little metal boxes.
Yeah, and inside that rectangular metal casing, there are actual physical platters, glass, or aluminum discs coated in magnetic material, and they're spinning at 5,400 or 7,200 revolutions per minute.
Inside the laptop.
Inside the laptop.
Yeah.
And a microscopic mechanical arm, called a read-write head, sweeps across these spinning platters, floating just nanometers above the surface to actually access your data.
See, putting highly sensitive, rapidly spinning disks and a microscopic needle into a device that gets, thrown into backpacks, dumped onto conference tables, used on turbulent airplane trays.
Right.
It just seems like a massive recipe for disaster.
It really is. Mechanical drives inherently conflict with the very concept of portability.
Yeah.
I mean, they suffer from thermal throttling in tight spaces. They consume considerable battery power just to physically spin the motor.
Oh, right, the motor drains the battery.
Exactly. And they're incredibly susceptible to shock. If you drop a laptop while the drive is writing data, that mechanical arm can literally crash into the platter, physically scraping away your data.
Oh, that's a nightmare.
Yeah.
But solid-state drives, or SSDs, eliminate all of that.
Entirely.
They use flash memory chips, zero moving parts. It immediately solves the thermal issue, the battery drain issue, and the physical shock vulnerability. But what really blew my mind in the A+ material is how the physical form factor of the SSD itself evolved to solve those space constraints we keep talking about.
Yeah, it's a great evolution. Because the first generation of laptop SSDs simply copied the old physical footprint.
Right, they just put flash memory inside the old box.
Exactly. They were built into those 2.5-inch rectangular boxes just so they could fit into the existing drive bays of older laptops.
What?
And they still required a SATA connection, which meant one cable for data transfer and a completely separate cable for power.
But modern laptops don't use that. They use the M.2 interface.
Right.
And it is just wild looking at an M.2 drive. I mean, it basically looks like a simple stick of chewing gum.
It really does.
Just a thin strip of circuit board with some black squares on it. It's honestly hard to reconcile that this tiny wafer holds an entire operating system, years of tax documents, family photos, massive software suites, whereas we used to need heavy metal bricks with spinning motors to do the exact same thing.
And do it much slower. The M.2 standard completely bypassed the physical and bandwidth limitations of those old 2.5-inch drives.
How so?
Well, because it plugs directly into the motherboard, it draws power and transfers data through a single slot. No extra cables.
Oh, nice.
More importantly, M.2 drives can utilize the NVMe protocol. That connects them directly to the PCIe of the motherboard.
Meaning what, exactly?
Meaning data flows at lightning speeds, bypassing the older, slower SATA controllers that were originally designed for those mechanical drives. And the installation is incredibly simple.
You just slide it in.
Yep. Slide the wafer into the slot at a slight angle until the copper pins are hidden, push it flat, and secure it with one tiny screw. That's it.
Okay, let me stop you right there, though, because this is where a lot of people hit a wall when they try to do this
Well, it's
themselves.
the software side of the upgrade.
Exactly. Let's say I want to do this upgrade. I have an older 2.5-inch drive running my operating system. I go buy a lightning-fast M.2 drive. The A+ notes recommend using cloning or imaging software, which is usually included for free by the SSD manufacturer.
Right.
You hook both drives up, run the software, and it creates a replica.
Yeah.
But here's my question. If I'm moving from a physical spinning disk on an old SATA connection to a brand new NVMe flash architecture, won't Windows just throw a massive fit when it boots up?
That's a really valid fear.
Right. Like, how does the operating system handle that massive hardware change without massive driver mismatches and blue screens of death?
That is a great technical question. So first, cloning software doesn't just drag and drop your visible files like a standard backup.
Who doesn't?
No, it performs a bit for bit, sector by sector replication. It copies the master boot record, the partition tables, the registry, literally everything.
Okay.
And as for that architectural shift from SATA to NVMe, modern operating systems like Windows 10 and 11 actually utilize something called a hardware abstraction layer.
Hardware abstraction layer.
Right. They have native built-in drivers for NVMe storage controllers. So when you boot the cloned M.2 drive for the first time, the operating system detects the new storage controller at a hardware level, loads the native generic driver for it, and boots up seamlessly.
Wow.
Yeah, the abstraction layer basically hides the physical hardware change from the software environment.
So you turn the machine back on, your desktop wallpaper is the exact same, your browser tabs are where you left them, but everything just happens 5 times faster.
Exactly. It really is the ultimate upgrade.
Okay, so we've packed all these tightly engineered, highly susceptible component into a densely shielded metal box, right?
Right.
The battery, the specialized cooling fans, the M.2 drives.
But
But how do you get a clean wireless signal out of a laptop chassis that essentially acts as a Faraday cage, just blocking radio frequencies?
it's a huge design challenge.
And here's where it gets really interesting,
Hmm.
because modern laptops have largely abandoned the physical Ethernet port just to save on thickness.
Yeah, you rarely see them anymore.
So they rely entirely on wireless cards, like Mini PCI or Mini PCI Express, which plug into the system board to provide your Wi-Fi and your Bluetooth. But the card itself isn't the antenna.
No, it's not. The wireless card generates and receives the radio frequency signal, sure. But if the antenna were confined to the card sitting at the bottom of the chassis, just nestled among metal plates and a massive lithium battery...
It would just block everything.
Exactly. The signal degradation would be incredibly severe.
So when you install one of these wireless cards, there are 2 tiny circular posts on it, a main connector and an auxiliary connector.
Yep.
And you have to snap these incredibly thin wires onto them. The A+ notes point out that these wires actually snake their way from the motherboard straight through the physical hinges of the laptop.
Which is crazy.
Right. And they are routed all the way up the sides of the display bezel, literally framing the screen itself.
It really is just an elegant solution to a physics problem. Radio antennas require elevation and a lack of physical obstruction to maximize their signal-to-noise ratio.
So by putting it in the screen,
Right. By embedding the antenna wires inside the plastic bezel of the screen, the moment you open the lid of the laptop, you are physically raising a radio tower above the interference of the motherboard and the desk beneath it.
that is so clever. And while we are looking at the top of that screen bezel, we really have to talk about what sits right in the center, the webcam and the microphone.
Oh, absolutely.
The notes specify that microphones are usually placed on the left and right of the camera lens to capture stereo audio. mostly for noise cancellation.
Hmm.
But this hardware isn't just for video conferencing anymore.
No, not at all.
It is basically the front line of localized security.
Yeah, because passwords are fundamentally vulnerable, right? To
Yeah.
social engineering, brute force attacks, you name it.
Yeah.
So the industry shift is heavily toward biometric authentication, leveraging the hardware that's already built into the device. The CompTIA material highlights Windows Hello Face and Windows Hello Fingerprint as the prime examples of this.
But the notes are very specific that you can't just use any standard, grainy 720p webcam to log into Windows Hello. It requires specialized hardware.
It does. A standard optical webcam only captures a two-dimensional image.
Right, just a flat picture.
Exactly. And if a security system relied on that, an attacker could simply hold up a high-resolution photograph of your face to the screen and completely bypass the lock.
Which would be terrible.
Right. So Windows Hello actually requires an infrared camera combined with a dot projector.
Like on phones?
Exactly. It projects thousands of invisible infrared dots onto your face, mapping the three-dimensional contours, the depth of your eye sockets, the bridge of your nose.
Wow.
It mathematically proves the geometry of a live three-dimensional human being, which renders a flat 2D photograph completely useless.
That is fascinating. And that mathematical proof of physical presence, it extends beyond biometrics, too.
Yeah.
The notes also heavily emphasize NFC, or near-field communication. Now, when most of us hear NFC, we think of, like, tapping a smartphone against a payment terminal to buy groceries.
Right, Apple Pay or whatever.
Okay.
That is active NFC, where your powered phone communicates with a powered terminal. But the A+ material focuses on its use in enterprise environments,
Like where?
like hospital workstations, manufacturing floors, secure warehouses. In these environments, NFC operates on the principle of electromagnetic induction.
Electromagnetic induction.
Yeah.
How does that induction actually authenticate someone in real life?
Okay, think of a nurse operating in a hospital wing. They might need to log into a totally different mobile workstation in every single patient room.
Okay.
Typing a secure, complex, alphanumeric password 20 times an hour is just an immense bottleneck.
Totally.
Instead, the laptop has a built-in NFC reader. The nurse wears a plastic ID badge with a tiny, unpowered microchip and an antenna coil embedded right inside it.
Unpowered, meaning no battery in the badge.
Exactly. When they tap that badge against the palm rest of the laptop's NFC reader generates a small magnetic field.
And that magnetic field physically interacts with the unpowered badge.
Precisely. The magnetic field actually induces a tiny electrical current in the antenna coil of the ID badge.
Wait, really? The field makes electricity in the badge?
Yeah. That fleeting current is just enough to power up the microchip for a fraction of a second, allowing it to transmit its secure credential back to the laptop's reader. And the range of this magnetic induction is strictly limited by physics to about 4 centimeters or less.
4 centimeters. So just like the infrared depth sensor proving a 3D face, the 4-centimeter limitation of NFC mathematically proves physical proximity.
Exactly.
You can't hack an NFC badge from the hospital parking lot.
You literally cannot.
True security on a portable device isn't just about a strong password. It's hardware-level proof that the authorized user is physically touching the machine.
When you synthesize all of these components, from the chemistry of the battery to the induction coils of an NFC reader, you realize that a laptop is really not just a shrunken desktop.
No, not at all.
It is a completely distinct computing paradigm, and it's governed entirely by the physics of miniaturization.
Well, we have covered a massive amount of ground today. We started by navigating the modularity lottery, seeing how lithium-ion polymer allows batteries to act as flat chemical space fillers, and how memory evolved from standard vertical sticks to highly compressed SODIMMs, or just disappeared into the motherboard entirely.
Right.
We looked at the thermal and kinetic reasons mechanical hard drives were abandoned for the lightning-fast gumstick profile of NVMe M.2 drives. And finally, we explored how the physical chassis itself acts as a radio tower for internal antennas, while using infrared depth mapping and magnetic induction to secure the data inside.
It's a lot, but understanding the mechanisms beneath the keyboard transforms that black box into a comprehensible system of trade-offs and really amazing engineering triumphs.
So here is your mission as you wrap up this deep dive. I want you to look up your specific laptop model specifications online. Look for a teardown video or the official service manual.
Highly recommend doing that.
Find out what you actually own. Is your RAM soldered to the board, capping your future performance? Is your battery modular, or is it glued into the aluminum? Empower yourself to know exactly what is sitting inside your bag right now.
And as you evaluate your own hardware, consider this final dynamic. Our consumer demand for laptops that are endlessly thinner, lighter, and more powerful is what drives the engineering we discussed today.
Right, we asked for it.
We do. But when manufacturers solder memory to boards and glue batteries deep into the chassis just to save 3 millimeters of thickness, the device becomes a sealed, disposable unit. We've achieved ultimate portability, but we must ask ourselves, are we passively trading away the basic right to repair, upgrade, and truly own the hardware we rely on?
That tension between cutting-edge portability and basic repairability is really going to be the defining hardware challenge of the next decade. Thanks for taking this deep dive with us.